Why does the Tabular method work for integration by parts, also known as the DI method or just the table method? So I'm assuming you already know about integration by parts. I just want to explain why the DI method works because people do wonder that. I think you'll see it's really just nothing but observing the pattern that always comes about from doing integration by parts and in figuring out the expressions ahead of time that always happen and then organizing them into a table. And that just streamlines the process and eliminates a lot of hassle and work involved in not being organized. So what I'm going to do here is I'm going to take our formula and I'm going to do these substitutions. So we have all of that here. So this is the integration by parts formula. So just kind of satisfy yourself that you're good with the substitutions, and we're going to go totally symbolic so we can more easily see the patterns that always happen that might not be as obvious as if you were, plugging in actual problems or algebraic expressions. So we start with this integral, and we know that we always do. So we're gonna take this integral and we're gonna do it the longhand way, and then we're gonna do it with the DI method, the table method, and we're gonna compare them and see they result in the same thing. So we know that we have to take our integral, we have to figure out this stuff. So we need to figure out a u and a dv. So I'm gonna make f correspond to u through this whole thing, and g correspond to v. So I'm making u this, and here's our dv. And then we know that we need to figure out this. So basically we take the integral, the derivative of both sides. I may say things backwards. Hopefully you'll know what I mean. I'll say derivative when I mean integral and vice versa. But anyway, if we take the derivative of both sides, we just get this, and then we multiply both sides by dx, and we get this. And then we take this, and really the only reason we want this is to get this. The important things are this, this, and this. Okay, so we take this, and so we want to work our way backwards to just v. So we take the integral of this, and we get this. And then notice that this is going to be u times v minus the integral of v du. So u times v, which is this, minus the integral of the row. So notice it's diagonal multiplication minus the integral of the row. So now we have this. So this has given us this. Now we have another integral, and maybe we need to keep going because it's still too difficult. And I'm going to keep going anyway just so we can see the pattern. So now we need to do another set for this. So this is going to be our u, and then this is going to result in a derivative higher, so a second derivative. And then our dv is going to be this and this. And again, we don't really care about this other than to get this. So to get from dv to v, we need to take the integral. Now that's this. Now I'm making up a notation of my own. It's not a thing. It's just something I'm doing for this video because we have nice notations for first, second, and third derivatives, but there really isn't a universal notation for first, second, and third integrals. So I'm just making this up. When I do this, that means this is the first integral of this. Okay, you'll never see it another time any other place. I don't, because I mean I'm not really planning to do that, but just so we're clear on that. Okay, so then from this we get this. So this is a leftover term from before. Now to get this from this, we're doing this times this, so diagonal multiplication. And that gives us this, and then we take the integral of the row. So the integral of v du, and here that is. Okay, now I'm going to get rid of the parentheses by distributing, and we're down to here. And now we're going to do the same thing again with this integral. I'm going to do basically 3 iterations. So we have our done terms. We need to take this and do another one of these. So we make this u. We get a derivative higher, and we make this our dv. And to get to just v, we have to take the integral of the integral. So this is going to be our second integral. And what I want you to notice here is that our DI table is going to be this stuff. So this and this would be the first row of our DI table we'll see in a minute. And then to get the second row of the DI table is going to be this. This is going to be the third row of the DI table. And this stuff is going to be the fourth row of the DI table. So we know those patterns are going to happen. So we just go ahead and do them ahead of time. And because we notice that we take our u and we get first derivative, second derivative, third derivative. And then our dv, we take this part, the DI table, we don't typically write the dx. We just take this part of it and we just integrate it. So we have g prime and then just g, and then integral of g and second integral of g. And so anyway, we'll look at that a little more later. But to finish up here our longhand method. So from this, we're just going to, so we have these two leftover terms, the done terms, and then this is going to come from this. So we have our diagonal multiplication, which gives us this minus the integral of the row. And that's as far as I'm going to take that. Now we're going to do the DI method, and we're going to show that we get the same thing. So what I'm wanting to compare is this and this. Okay, so like I said, we find our first u and our dv. We don't write the dx because we only need that if we're going to do an integral, and we would write that in if we need to form the integral. And so this we just keep differentiating, and this we just keep integrating. And then to form this, it's just going to be this times this minus the integral of this. If we were going to stop here, okay, this would be our u times v minus the integral of v du. That would be one iteration. But if we want to keep going, then, you know, our stopping integral might be this times this. Again, u times v minus the integral of v du. Or if we want to keep going and producing all these terms, and, you know, this might be our final integral. So what we have here is this times this. So let me just do this. So this times this gives us our first term. This times this gives us our second term. This times this gives us our third term. And our final integral is just going to be from this row. And you'll notice it gives us the exact same thing as this. So then it's just really a matter of knowing when to stop. But that's going to be the same times you would have stopped if you were doing it longhand. So one of those ways might be, you know, if this is a 0, or, you know, maybe this is a 0. So you just do this times this, done, because your integral is going to be a 0 integral. So in that case, you don't have any more integrals to do. Another way you might stop is you do this times this, and then maybe this, you know, your first iteration, maybe that's an easy integral, so you just do it and you're done. The other way that you would stop is if you happen to notice, okay, this integral happens to be the same as this, in which case I'm not going to go into how you do that, but in that case, you don't actually even need to do the integral. You eliminate it through an algebraic process. But hopefully this will make you a little more comfortable with why the table method works in the first place. I meant to address these as well. So the reason we put those there, you can see the pattern. So plus, minus, it just alternates. And that just comes from this subtraction in the formula itself. So you do want to make sure that your multiplications are using these signs as well.